Hello viewers on YouTube. In this video tutorial, we are going to consider electric potential and electric potential difference. We are also going to consider the formula that helps us to determine the magnitude of each of these quantities, and most of all, what actually distinguish them. So let's start with electric potential. Symbolically, we represent electric potential with uppercase V, and by definition is the potential energy per unit charge, is the electric potential energy per unit charge, to be precise. So if we represent this mathematically, it means V is equal to PE, where PE is the electric potential energy then per unit charge, divided by the magnitude of a charge. The electric potential is measured in volts, and what 1 volt of electric potential tells us in essence is that in 1 coulomb of charge we have 1 joules of energy. That's what makes sense. So that's how to determine the electric potential of a certain charge in an electric field. So it means it is important for you to know how to determine the electric potential energy of a charge relative to its position in an electric field. If you are interested, feel free to check out the video in the description, as I have video on that. And also, you can at the same time click on the video that is pop up at the top right hand corner of this video. So whichever way, you will find the video. However, for review, to determine the magnitude of the electric potential energy, of a certain charge in an electric field relative to its position, then the formula that helps us to do that is such that PE is equal to the product of the magnitude of the electric field, the magnitude of the charge, and the position of that charge from the negative charge plates. So it's something you might want to keep in mind, as you might later on use it as we progress forward in this video. So now that you know how to determine and what electric potential is in essence, what about electric potential difference? We represent that with delta V, which tells us change in V, that is change in electric potential. And without any further ado, we should know that what it tells us in essence is that it tells us the change in the electric potential energy per unit charge. As the position of the charge changes from one point to another in an electric field, its electric potential energy will change. And as a result of this, its electric potential will also change or undergo changes. So therefore, the change in electric potential is simply the change in potential energy divided by Q. And if we express this forward, it means PEB, if we are considering point B and A, divided by Q, the minus PEA over Q. Perfect. If we are considering the change, the point BAB, if the charges changes from point A to point B, then the change in potential energy will be PB minus PA. So now if we factor out 1 over Q, we have 1 over Q multiplied by PEB minus PEA. Now the change in potential energy is simply equal to negative W, where W is the electrical work done. Actually explain more further in the video, but since we just really need the concept here, we don't have to dive more into that. If you actually want to know why, then you might want to check out that video. So it means this is 1 over Q times negative W, and therefore we have the change in electric potential to be equal to negative W divided by the magnitude of the charge. Perfect. So we have another formula that you have to keep in mind. So as we are forming each of these formulas, we will be putting them at somewhere at the top right hand side corner, so in case you might later want to use them. So we have PE by Q, just for review, and we have delta V to be equals to negative W over Q. Now for this formula to work fine, it is important for you to put the sign associated with the charge into consideration. That is, let that sign take its effect. If the magnitude of the charge is associated with a negative sign, plug in the value along with the negative sign. so that at the end of the day, the minus will cancel out and we will have a positive change in electric potential. And when this occurs or takes place, it means that the charge moves from a low potential to a high potential. But when the electric potential difference is negative, it means the charge has moved from a high potential to a low potential. Am I communicating? Perfect. So it's important to actually put into account the sign associated with the magnitude of the charge. So now let's try to form more further formulas that we might later need to make use of in solving problems involving also one of my tablets. Now, if you could recall, we said that work done, typically electric work done is the product of the electric force and distance between the charge and a test point, or from the negative charge plate. Then it means that if F is equal to the product of the electric field and the magnitude of the quantity of charge according to electric field, then it means the electric work done is the same as the product of the magnitude of the electric field, the magnitude of the charge, and the distance of the charge from a certain point. However, from this equation, we can as well as isolate W. In fact, W will be equals to negative Q times delta V. Since W is equal to the same thing, then why not set them to be equal? And this implies that negative Q delta V, where delta V is the electric potential difference, very, very important, not the electric potential, okay, is equal to EQD. Now, since we are considering the same charge, it means the magnitude of the two charges cancels out. And if they cancel out, then we have negative change in electric potential to be equal to ED. And this is the third formula we have to put into consideration. However, this formula can be manipulated in such a way that if we have the potential difference, electric potential difference, and the distance of the charge from a certain point, we can as well as determine the magnitude of the electric field, that will be negative delta V divided by T. Okay, so those are the formulas you have to be familiar with, and that's it. So now let's consider some examples in order to make use of these formulas effectively. Example number 1. A negative 40 nanocoulombs charge is located at a point where the electric potential is 2000 volts. What is the electric potential energy of this charge? Feel free to pause the video and figure this out if you want to. Now, we are given the electric potential to be positive 2000 volts. And we also have the magnitude of the charge Q to be negative 40 nanocoulombs. The electric potential is in volts, which makes sense as it's already in appropriate unit. But for the charge, we have to make an adjustment. So we need to multiply with 10 to the power of negative 9. You know, to get rid of the nano, and then we see how it coulombs. If you want, you can express this more forward as 4.0 times 10 to the power of negative 8 coulombs. Excellent. So now remember, the electric potential is equal to the electric potential energy per unit charge. So upon solving for PE, we can have PE, electric potential energy, to be equal to the product of the electric potential and the magnitude of the charge. And finally, upon substitution, we have 2000 multiplied by the magnitude of the charge is negative 4.0 times 10 to the power of negative 8. So we're going to type this into our calculator. So I have 2000 multiplied by 4 multiplied by 10 to the power of negative 8. And with that, I got 0.00008, which is the same as 8.0 times 10 to the power of negative 5. So since this potential energy, I can put joules. This is our solution to example number 1. On to example number 2. However, don't forget the negative sign, very important. So, well, if you're dealing with the multiple choice questions and you realize there's no negative sign, just select whatever you see. So far, you are having the same magnitude. So that's it. On to example number 2. A Van de Graaff generator has a charge of 5.0 times 10 to the power of negative 6. Okay, this should be charge, not change. Calculate the electric potential at a distance of 0.5 meter away from the center of the generator. So what do we have? We have a quantity of charge Q to be 5 times 10 to the power of negative 6 coulombs. Excellent. Then we have the distance R to be 0.5 meter. So what do you think we can do in order to find the electric potential of the charge at distance 0.5 meter? Pause the video and figure this out yourself. Now, if we recall, we said the electric potential V is equal to the potential energy divided by the quantity of charge. Also, we said the potential energy of a charge relative to its position is expressed as the magnitude of the electric field times the magnitude of the charge times its distance from a certain point or from the negative charge plate. So that will be y. Now, the distance over here is 5. So let's just assume it's r instead of y. Let's put r. So that's the potential energy. So we were not given the magnitude of the electric field, but we know that electric field E is equal to kq over r squared. Okay, where k is the Coulomb's constant. So it means that we can have kq, okay, let me use uppercase letter, kq times q times r divided by r squared. Now this will reduce this and this will become squared. This means the electric potential energy becomes kq squared divided by r. Excellent. So now let's find the electric potential. So it means finally V will be kq all squared over r multiplied by 1 over q. So for those of you wondering, it is divided by q. So if you divide it by q, it's the same thing as multiplying with 1 over q. Okay, so 1q will reduce and we'll have our electric potential V to be equal to kq divided by r. So this is our electric potential. We can now plug in our values. The value of k is a constant. Remember, 9.0 times 10 to the power of 9. Then the magnitude of the charge is 5 times 10 to the power of negative 6. And the distance is simply 0.5. And finally, we have our electric potential V to be equals to, so we need to use our calculator for that. That's going to be 9 times 10 to the power of 9 multiplied by, okay, multiplied by 5 times 10 to the power of negative 6, and finally multiply by 0.5. So I end up having 22,500, which is 2.25 times 10 to the power of 1, 2, 3, 4 to the power of 4. So since this electric potential has been measured in volts, and this is our final answer to this problem. I hope you understand. On to example number 2. Sorry, number 3. An electron is moved from a point in an electric field where the electric potential is 1.9 joule per coulomb to another point where the electric potential is 2.0 joule per coulomb. Calculate the electric potential difference, okay, not just potential difference, electric potential difference between the 2 points in the electric field, and hence determine the work done in moving the electron. So feel free, pause the video and try this question out. So we can say, okay, since the charge is moving from point A to point B, so let point A be VA, and VA, let it be positive 1.9 joule per coulomb. If you want, you can decide to move your charge from point X to Y regardless. But you know that if you are moving from point X to Y, Vx is one of the common force, and which will be the one you have to attach 1.9 joule per coulomb to. So Vb is now 2.0 positive joule per coulomb. Perfect. So the goal is to determine the electric potential difference. Remember, change in electric potential, which is electric potential difference, is simply VB minus VA. That's going to be 2, since they are both positive, the minus 1.9. When we do this, we should have 0.1 joule per coulomb. That's it. That's the electric potential difference between point A and point B, where point A has an electric potential of 1.9 and point B has an electric potential of 2.0. Now what about the work done? That's when we have to make use of some of the formulas we discussed at the beginning of this video. Remember, we said that the work done is simply equals to the product of the magnitude of the electric potential difference and the magnitude of the charge. However, the negative sign must not be omitted. So now, what is the charge? What would you say? Well, the problem is emphasizing on electron, and we know that the magnitude of electron is constant. It means even without we being given, then we should know what it is, because they expect us to know what it is. So that would be negative 0.1 times the magnitude of electron is 1.6 times 10 to the power of negative 19. And if we do this math, 0.1 times 1.6. So we have 0.16, which is the same as negative 1.6 times 10 to the power of negative 10. And that is the electric work done in joules, okay, in moving the charge from point A to point B. That's the solution to this example number 3. By now you should have been getting used to how to approach problems involving either electric potential or electric potential difference. On to example number 4. A 9.0 volt battery is connected between two parallel metal plates 4.0 mm apart. What is the magnitude of the electric field between the plates? Well, we have our delta V, which is the electric potential difference to the 9.0 volts. You might be wondering, why did I choose the 9.0 to be delta V? Well, because 9.0 volt battery means the voltage of the battery, that is, the potential difference between its terminal. Okay, you can have as much as possible charges in the battery, but remember, electric potential is only for unit charge. We only want to determine the amount of energy, okay, stored or withstand in a unit charge. But we can have as much as possible charge in the battery, so you are having the potential difference, okay, the voltage. Perfect. So now we're given the distance between the metal plate, that be R to be 4.0 millimeter, which can express as 0.004 meter. And the goal is to determine the electric field E. So what would that be? Now you can also see out the same thing as D. Remember, we formed the formula that the electric field E is the same thing as the ratio of the electric potential and the distance D, or R, whichever the case might be. And so therefore, upon substitution, we now have 9 divided by 0.004. And also, don't ever forget the negative. Negatives that are attached to it. And if we divide this using our calculator, we would end up having 9 divided by 0.004 got 2,250, which is the same as 2.25 times 10 to the power of 1 to 3 to the power of 7. Selective field measured in Newton per coulombs. And that's our solution to example number 4. This is how to easily approach problems involving electric potential and electric potential difference. I hope you find this helpful and understandable. Thanks for watching. See you in the next video. So consider using this example number 5 as a practice problem. Feel free to share your solution with me via the comment section below. Bye for now.